In December of 2004, something happened 50,000 light-years away from Earth. A star, already dead, already compressed beyond anything in ordinary physics, cracked. A fracture opened across its surface, and in 1/10 of a second, it released more energy than our Sun will emit in the next 250,000 years. The burst of radiation crossed 50,000 light-years of space, reached our solar system, and hit Earth. It compressed our ionosphere. It disrupted the magnetic field signatures that satellites use to navigate. It was detectable from the surface of the planet. Astronomers had instruments pointed at it, and the signal was so bright it saturated their detectors. Instruments designed to measure some of the most energetic events in the cosmos were overwhelmed. If this object had been 10 light-years away instead of 50,000, the event would have triggered a mass extinction. It was, from our safe remove across the galaxy, the brightest burst of radiation from beyond our solar system ever recorded in human history. The object responsible was about 12 miles across. It was a magnetar. And what happened that December night is not even close to the strangest thing about them. To understand magnetars, you have to first understand the death of stars. Because magnetars are born in one of the most violent events the universe produces. Stars are not permanent. They are engines running on fuel, and when the fuel runs out, the engine fails. The way a star dies depends almost entirely on how much mass it has. Stars like our Sun will eventually exhaust their hydrogen, swell into red giants, shed their outer layers into beautiful shells of glowing gas called planetary nebulae, and leave behind their hot, compressed cores as white dwarfs. Objects about the size of Earth, dense but not catastrophically so, slowly cooling over billions of years into cold, dark remnants. That is a relatively peaceful death, cosmically speaking, but for stars significantly more massive than our Sun, stars with at least 8 to 10 times the Sun's mass, and sometimes far more, the ending is not peaceful at all. When the fuel in their cores runs out, gravity wins instantly and completely. The outer layers of the star, no longer supported by the outward pressure of nuclear fusion, collapse inward at a significant fraction of the speed of light. In a fraction of a second, the core is compressed from something the size of Earth to something the size of a city. The infalling outer layers hit this suddenly rigid core and bounce outward with tremendous force, generating a shockwave that tears the star apart in a supernova, one of the most energetic events in the known universe. For a brief period, a single supernova can outshine an entire galaxy of hundreds of billions of stars. The energy released in a few seconds is staggering beyond any intuitive grasp. What remains after all of this, the collapsed core, depends on how much mass the original star had. For stars in a certain mass range, the core survives as a neutron star. Neutron stars are among the most exotic objects in physics, and they deserve a moment of attention before we get to magnetars. Because a magnetar is a specific and extreme variety of neutron star, and you cannot appreciate the magnetar without first appreciating just how extreme the baseline already is. A neutron star typically contains between 1 and 2 times the mass of our Sun packed into a sphere roughly 12 to 15 miles across. Think about that. The entire mass of our Sun, a ball of gas nearly 1,000,000 miles in diameter, compressed into something smaller than a medium-sized city. The result is an object with a density that shatters every intuition about what matter can be. A teaspoon of neutron star material would weigh approximately 10 million tons. Not 10 million pounds. 10 million tons. You could compress every human being who has ever lived into a volume smaller than a sugar cube and still not approach the density of neutron star interior. If you somehow transported a golf ball-sized piece of a neutron star to the surface of the Earth, its gravitational pull would be catastrophic, and its weight would be almost incomprehensible. The interior of a neutron star is so compressed that the ordinary structure of matter has completely broken down. In normal matter, in rocks, in air, in your body, atoms consist of a nucleus surrounded by electrons, with enormous amounts of empty space relative to the nucleus itself. In a white dwarf, gravity squeezes the atoms together, but they maintain their basic structure. In a neutron star, gravity has gone so much further that it has overcome the forces that keep electrons separate from nuclei. The electrons have been forced into the protons, combining to form neutrons, hence the name. The star is essentially a gigantic atomic nucleus, a sphere of neutrons packed together under almost unimaginable pressure. The physics of the interior is still not fully understood. There may be exotic states of matter in the deep interior, regions where even neutrons have broken down into their constituent quarks, forming what theorists call strange quark matter or quark-gluon plasma. These are not settled questions. The interior of a neutron star is one of the most extreme environments in the known universe, and our physical theories are genuinely strained by the attempt to describe it. Neutron stars also rotate. They rotate extraordinarily fast because of the conservation of angular momentum, the same principle that makes a spinning figure skater speed up when they pull their arms inward. The original massive star was rotating, probably relatively slowly, and when its core collapsed from something Earth-sized to something city-sized, all of that rotational momentum was conserved in a dramatically smaller package. The result is neutron stars that can spin hundreds of times per second. Some of the fastest rotating neutron stars, called millisecond pulsars, complete over 700 full rotations every second. The surface of such a star is moving at a significant fraction of the speed of light. These are solid objects spinning faster than a kitchen blender, except each one contains the mass of the sun. Neutron stars also have magnetic fields. This is where we begin the journey toward magnetars, because the origin of their extraordinary magnetic properties lies in the same process, the collapse and compression of the stellar core. Stars have magnetic fields, generated by the motion of charged plasma in their interiors. When the core collapses, those magnetic field lines are compressed along with everything else. A magnetic field's strength increases when the area threading through it decreases. This is a consequence of the fundamental geometry of magnetic flux. As the core shrinks from Earth-sized to city-sized, the area threaded by the magnetic field decreases by an enormous factor, and the strength of the field increases correspondingly. Typical neutron stars end up with magnetic fields roughly 1 trillion times stronger than Earth's, already extraordinary by any ordinary measure. Earth's magnetic field is about 0.5 Gauss. A typical neutron star has a magnetic field of around 10 to the 12th Gauss, 1 trillion Gauss. And even this, which would be the most extreme magnetic field reachable by any human technology by an almost infinite margin, is the ordinary baseline for neutron stars. Magnetars have magnetic fields that are stronger than typical neutron stars by a factor of 1,000 or more. Their magnetic fields reach 10 to the 15th Gauss, a quadrillion Gauss, or 10 to the 15th times stronger than Earth's. These are numbers that require some unpacking to appreciate, because the human mind did not evolve to intuitively grasp fields of this strength. So let us try to make it concrete. The strongest magnetic fields ever produced in a laboratory, using the most powerful electromagnets ever built, which require enormous amounts of electricity and can only be maintained for fractions of a second before the equipment is destroyed, reach around 100 Tesla, or about 1 million Gauss. That is the absolute limit of what human technology has managed to achieve. A magnetar's field is roughly 1 billion times stronger than that. And unlike a laboratory electromagnet that exists for milliseconds, a magnetar's field is permanent, embedded in the structure of the star itself, and has been sustained for thousands or millions of years. At such field strengths, matter itself behaves in ways that have no analog in ordinary experience. The magnetic field of a magnetar is so strong that it distorts the shapes of atoms. Atoms in a magnetic field experience the Zeeman effect. The field shifts the energy levels of electrons orbiting the nucleus. In ordinary circumstances, this is a very small effect, used in spectroscopy to identify magnetic fields in distant objects. In the fields around a magnetar, it is not a small effect. The energy of the magnetic field is so much larger than the energy of electron orbits that the atoms are squeezed into long, thin cylinders aligned along the magnetic field lines. The electrons, instead of occupying roughly spherical probability clouds around the nucleus as they do in normal matter, are constrained to one-dimensional structures, quantum states aligned along the field. Atoms in the atmosphere of a magnetar are 1,000 times longer than they are wide. The chemistry of such material, if you could call it chemistry, has no relation to anything in ordinary experience. At even shorter distances from the magnetar, the field is strong enough to do something that sounds like pure science fiction but is a real prediction of quantum electrodynamics, the most precisely tested theory in the history of physics. The vacuum itself becomes polarized. Empty space, in the presence of such an extreme magnetic field, develops optical properties. Light traveling through the vacuum near a magnetar is split into two polarization modes that travel at different speeds, a phenomenon called vacuum birefringence. This was first predicted theoretically in the 1930s and has now been observationally confirmed around at least one magnetar. The vacuum is not truly empty. It seethes with virtual particles, pairs of particles and antiparticles constantly flickering in and out of existence, permitted by the uncertainty principle as long as they annihilate before they can be directly detected. In an extreme enough magnetic field, these virtual pairs can be affected by the field in ways that give the vacuum measurable electromagnetic properties. The quantum structure of empty space is directly observable near a magnetar. This is not metaphor, this is measurement. The surface of a magnetar, if you could somehow approach it, which you cannot survive doing by the time you are anywhere close, would be the most alien environment imaginable. The surface gravity is roughly 200 billion times Earth's surface gravity. If you were standing on the surface of a neutron star and you stumbled and fell, you would hit the ground at roughly 2,000 miles per second. The surface itself is a crystalline lattice of neutrons and atomic nuclei, compressed into a material harder than anything that exists anywhere else in the known universe. The crust of a neutron star is roughly 10 billion times stronger than steel. This is the structure that, under the influence of the magnetar's colossal magnetic field, occasionally cracks. When the crust of a magnetar fractures, a starquake as it is often called, the rearrangement of the magnetic field releases a tremendous burst of energy. The magnetic field lines, which had been distorted by the stresses in the crust, suddenly relax into a lower energy configuration. That released energy propagates outward as a flash of gamma rays and X-rays, intensely bright and intensely brief. Some of these events last only fractions of a second. Others, called giant flares, can last for minutes and produce energies that dwarf anything else in the known universe outside of gamma-ray bursts. The giant flare of December 2004 came from a magnetar designated SGR 180620, sitting in the constellation Sagittarius, roughly 50,000 light-years from Earth, on the other side of the Milky Way. In a 5-minute period, it released more energy than our Sun emits in 250,000 years. The initial burst, a mere fifth of a second of peak emission, was so bright that it ionized Earth's upper atmosphere to a depth comparable to daytime conditions on the night side of the planet. Our ionosphere, which normally behaves differently on the day and night sides because of solar radiation, was briefly made uniform across Earth's entire surface by radiation from a dead star on the other side of the galaxy. The event was visible to spacecraft throughout the solar system. Instruments that were not pointed at it were still affected by the secondary effects. It remains the most powerful event from beyond our solar system ever directly observed by humans. Had SGR 18620 been positioned 10 light-years from Earth, which, for context, is a relatively short distance in galactic terms, Alpha Centauri is about 4 light-years away. The radiation from this single flare would have been sufficient to cause a mass extinction event comparable to the ones that have periodically wiped out most life on this planet throughout geological history. The ozone layer would have been catastrophically depleted. The DNA of surface life would have been subjected to lethal doses of gamma radiation. The event would have been visible in broad daylight as a point of light brighter than the sun for a brief, terrifying period. This is not a theoretical catastrophe. It nearly happened. Not to us. We were safe at 50,000 light-years. But to whatever might have been living around stars near SGR 180620 when it flared. And the fact that magnetars exist, distributed throughout our galaxy, is a reminder that the universe contains hazards that operate on scales and through mechanisms that have nothing to do with anything in our local cosmic neighborhood. Astronomers currently know of about 30 magnetars in the Milky Way, though the true number is almost certainly much higher. Magnetars are not permanent. They are a phase in the life of a neutron star, not a final state. The extraordinary magnetic field that defines a magnetar decays over time because maintaining such a field requires energy, and the star radiates that energy away. The timescale for a magnetar's field to decay to the levels of an ordinary neutron star is roughly 10,000 years. So at any given moment, only a small fraction of the neutron star population is in the magnetar phase. Over the history of the galaxy, there have been many more magnetars than currently exist. The ones we observe are the currently active ones, the ones whose fields are still in the process of decaying, and they are identifiable primarily because their strong fields drive distinctive X-ray and soft gamma-ray emission that ordinary neutron stars do not produce. The formation of magnetars is not fully understood. Not every massive star that goes supernova produces a magnetar. Current theories suggest that the extreme magnetic fields of magnetars arise from a specific set of conditions during the collapse of the stellar core, Rapid rotation and turbulent convection in the protoneutron star combine to act like a dynamo, amplifying the magnetic field to extraordinary levels in the first seconds of the neutron star's existence. The rotation and the convection together drive electrical currents through the hot, conducting interior, and those currents generate and amplify the field in a self-reinforcing process called a dynamo mechanism, similar in concept to what drives Earth's magnetic field, but operating at incomparably higher energies. The specific stellar parameters that produce a magnetar versus an ordinary neutron star are still being worked out. This is an active area of theoretical and observational research. Magnetars may also be connected to one of the greatest unsolved mysteries in modern astrophysics: fast radio bursts. Fast radio bursts, or FRBs, are millisecond flashes of radio waves that arrive from cosmological distances, carrying energies in some cases comparable to what the sun emits in days or weeks, all released in thousandths of a second. They were first discovered in 2007 in archival data from the Parkes Radio Telescope in Australia, and for years their origin was entirely unknown. The flashes were too brief and too energetic and came from too many different directions to fit neatly into any existing category of known astrophysical phenomena. In 2020, astronomers detected a fast radio burst from within our own Milky Way, which was an extraordinary development because it allowed the source to be precisely identified for the first time. The source was a magnetar, SGR 1935+254, which simultaneously produced an X-ray flare and a burst of radio waves whose properties were consistent with what had been observed from cosmological FRBs. This was a major breakthrough. It provided strong evidence that at least some fast radio bursts, and possibly all of them, are produced by magnetars, either through the starquake mechanism or through some interaction between the magnetar's extreme field and its surrounding environment. The exact mechanism is still being debated, but the connection between magnetars and FRBs, if confirmed fully, would close one of the biggest mystery source gaps in observational astronomy. The significance of this potential connection is difficult to overstate. Fast radio bursts are detected at cosmological distances. Some come from galaxies billions of light-years away. If magnetars produce them, then the most energetic radio flashes in the observable universe, events that briefly outshine everything else in the radio sky across billions of light-years, are produced by objects that are 12 miles across and were born in a stellar explosion. The ratio of physical size to energy output is almost incomprehensible, and the same objects that disturbed Earth's ionosphere from across the Milky Way in 2004 may be responsible for the most distant and energetic radio transients ever detected. There is another connection that magnetars may have to extreme cosmic events, one that ties them to the most energetic explosions in the universe. Gamma-ray bursts are brief flashes of gamma radiation that, for a few seconds or minutes, outshine the entire observable universe. There are two main types: short gamma-ray bursts lasting less than 2 seconds, and long gamma-ray bursts lasting longer. Short gamma-ray bursts are now confidently associated with the merger of two neutron stars, a violent collision and merger that also produces gravitational waves and a kilonova, and which is one of the primary sites in the universe where heavy elements like gold and platinum are forged. Long gamma-ray bursts are associated with the collapse and explosion of massive stars, hypernovae. In both cases, magnetars may play a role. Some models suggest that the extreme energy output of certain gamma-ray bursts is driven not just by the initial explosion, but by the spin-down of a rapidly rotating magnetar born in the event, the magnetar radiating its rotational energy into the surrounding material and powering the extended gamma-ray emission. Whether this is the correct model for any specific observed gamma-ray burst is still being worked out, but the possibility places magnetars at the center of the most energetic events in the known universe in multiple distinct ways. Let us pause and consider what we have established about these objects. They are city-sized. They contain the mass of the sun. They rotate rapidly. Their gravity is 200 billion times Earth's. Their crusts are 10 billion times stronger than steel and occasionally fracture anyway. Their magnetic fields are strong enough to distort the shapes of atoms and give the quantum vacuum measurable electromagnetic properties. They produce flares that can cross the galaxy and affect Earth's ionosphere. They may be the engines behind fast radio bursts detectable from billions of light-years away. They may power some gamma-ray bursts. They live at the absolute edge of what matter can be while still being matter. The question of what lies beyond the magnetar in terms of density and compression, is itself a profound open question in physics. We know what neutron stars are in broad terms. We have equations of state, mathematical descriptions of how matter behaves under extreme pressure, that predict the properties of neutron star interiors. But those equations of state are uncertain, especially for the deep interior where the densities exceed what can be replicated in any laboratory. There may be a transition at some depth from ordinary neutron matter to a phase where the neutrons themselves dissolve into their constituent quarks. There may be strange quark matter, containing strange quarks in addition to the up and down quarks that make up ordinary protons and neutrons. There may be color superconducting phases, exotic states in which quarks pair up in ways analogous to electron pairing in superconductors. Some theorists have proposed that there exist strange stars, objects made entirely of strange quark matter, which would be even denser than neutron stars. Whether these phases exist and under what conditions is one of the most important open questions in nuclear and particle physics, and neutron stars, especially the most extreme ones, including magnetars, are the only natural laboratories in which these conditions occur. The maximum mass that a neutron star can have is another critical open question. Above a certain mass, no known force can resist gravity, and the neutron star must collapse further into a black hole. Where exactly that threshold is depends on the equation of state of dense matter, which, as noted, is still uncertain. Observations of neutron stars with high masses, some confirmed to be around 2 solar masses, have already ruled out certain equations of state, constraining the physics of dense matter in ways that theoretical calculations alone cannot. Magnetars, as extreme members of the neutron star family, are part of this broader project of using astronomical observations to probe the behavior of matter at densities unreachable in any terrestrial experiment. The detection of gravitational waves from neutron star mergers, made possible by the Laser Interferometer Gravitational Wave Observatory, LIGO, and its sister observatory Virgo, has added a remarkable new dimension to neutron star science. In 2017, the first direct detection of gravitational waves from a neutron star merger, designated GW1170WANE7, was accompanied by a short gamma-ray burst, a kilonova visible in multiple wavelengths, and the detection of heavy elements being synthesized in the merger. This single event confirmed multiple theoretical predictions simultaneously and opened the era of multi-messenger astronomy, in which the same event is studied through gravitational waves, light across the electromagnetic spectrum, and potentially neutrinos simultaneously. What the merger left behind, whether a heavier neutron star, a magnetar, or a black hole, is not fully determined, and understanding the remnants of neutron star mergers, including their magnetic properties, is an active area of research that bridges astrophysics, nuclear physics, and gravitational wave astronomy. The connection between magnetars and heavy element synthesis is worth dwelling on. When neutron stars, including magnetars, form in supernovae, the conditions in and around the explosion are sites of rapid neutron capture, one of the primary processes by which elements heavier than iron are forged. The extraordinarily neutron-rich material ejected from a magnetar-forming supernovae may play a specific role in nucleosynthesis, the creation of elements that differs from ordinary neutron star supernovae because of the additional energy injection from the magnetar's spin-down radiation. Every gold atom that exists in the universe was forged in an environment of extreme neutron density and extreme violence. Some of those environments may have been the births of magnetars. The ring you wear, if it contains gold, may contain atoms whose nuclei were assembled in the first seconds after a magnetar's birth. The future of magnetar science is tied closely to the future of multi-wavelength and multi-messenger astronomy. Current and near-future X-ray observatories, including missions like NICER, NuSTAR, and the proposed future missions like the Enhanced X-ray Timing and Polarimetry mission, are designed in part to study neutron stars and magnetars in extraordinary detail. The ability to measure the X-ray pulse profiles of magnetars with high precision allows astronomers to model the geometry of the star's magnetic field and the structure of its hot surface regions. Polarimetry, measuring the polarization of the X-rays, provides additional constraints on the geometry and on the exotic optical properties of the vacuum near the magnetar. Future gravitational wave detectors, with improved sensitivity over current LIGO Virgo capabilities, may eventually be able to detect the oscillations of neutron star crusts following a giant flare, effectively listening to the seismic aftermath of a magnetar starquake from Earth using space-time itself as the medium for the sound. Radio telescopes like CHIME in Canada and the Square Kilometre Array currently under construction are providing and will continue to provide enormous datasets of fast radio bursts, some of which are repeating, which has allowed detailed studies of their emission properties and the environments from which they come. As the sample of known FRBs grows from the thousands currently known to potentially millions with SKA, the statistical properties of the population will tightly constrain whatever physical mechanism is producing them. If magnetars are the answer, and current evidence strongly suggests they are at least a major contributor, then the FRB population is effectively a census of magnetar activity across the observable universe, probing billions of years of cosmic history. There is something almost mythological about magnetars, in the sense that the extremity of their properties strains the limits of language. We say their magnetic fields are quadrillion Gauss and we move on. But it is worth sitting with what that number implies. The interplay between matter and electromagnetism is the foundation of all chemistry, all biology, all ordinary experience. Everything that has ever happened on Earth at the human scale happens because electromagnetic forces mediate the interactions between atoms, holding molecules together, driving chemical reactions, allowing proteins to fold and cells to function and neurons to fire. A magnetic field of the strength found in a magnetar would simply overwhelm all of that. It would distort the electron orbitals that chemistry depends on. It would change the fundamental electromagnetic architecture of matter. There is no life, no chemistry, no ordinary material physics in the environment of a magnetar, only the raw interaction of compressed nuclear matter and electromagnetic fields at energies that belong to the interior of particle accelerators, or the first moments after the Big Bang. And yet these objects exist. They are out there in our galaxy right now, spinning in the dark, their extraordinary fields slowly decaying over thousands of years, their crusts occasionally cracking and releasing bursts of radiation that ripple across the galaxy. They formed from stars not fundamentally different from the stars we see overhead every night. The sun is not destined to become a magnetar. It lacks the mass, but the more massive stars visible in the night sky, the bright blue supergiants that anchor the great constellations, many of them are candidates. Betelgeuse, the red supergiant that forms the left shoulder of Orion, has enough mass that when it dies, which could happen any time in the next 100,000 years, essentially immediately in astronomical terms, it may leave behind a neutron star. Whether that neutron star would be a magnetar would depend on conditions at the moment of collapse that we cannot predict precisely. But the Orion constellation that human civilizations have been watching for tens of thousands of years, that sailors navigated by and farmers used to mark the seasons, contains within it a star that is approaching the end of its life, and that may one day, in the blink of a cosmic eye, explode and leave behind one of the most extreme objects in the universe. The night sky is not static. It only appears static on human timescales, which are far too short to catch the dramatic events that are constantly reshaping the galaxy on longer scales. Right now, somewhere in the Milky Way, there are neutron stars in the magnetar phase, spinning and crackling with magnetic energy, producing X-ray emission that our telescopes detect and catalog. Some of them may produce giant flares in our lifetimes. Most of them are far enough away that even a giant flare would pose no threat to Earth. The 2004 event from 50,000 light-years was remarkable precisely because it was close enough to be detectable at the surface, which is unusual. The known magnetars are scattered across the galaxy at various distances, most of them safely remote. But the broader point, that the universe contains objects with properties this extreme, operating by physics this alien, and that some of them are sitting inside our own galaxy, inside the same spiral structure that our sun calls home, is worth dwelling on. We live in a galaxy that contains among its hundreds of billions of stars and the remnants of billions of dead stars, some of the most exotic objects in the known universe. Not in distant galaxies, not at the edge of the observable cosmos, but here, among us. In the same stellar neighborhood, in the same gravitational structure that our sun inhabits, there are city-sized spheres of nuclear matter spinning in the dark with magnetic fields strong enough to warp the quantum vacuum and sending occasional flares of radiation racing across the galaxy at the speed of light. The universe is not a gentle place. It is wild and violent at scales we cannot feel but can, with effort, measure, and comprehend. And magnetars are perhaps the clearest, most visceral example of that wildness. Objects that could not possibly be more extreme while still being made of matter, still being subject to the same laws of physics that govern the atoms in your body, still being real and observable and present in our cosmic backyard. They are the most powerful magnets in existence. They are the densest material objects in the universe. They are born in the depths of stars, and they die by slowly leaking away their extraordinary energy into the surrounding cosmos, eventually fading to the level of ordinary neutron stars, their magnetar phase complete, their most dangerous moments behind them. We detected one from 50,000 light-years away, with instruments not designed for an event of that scale, and we learned more from that 5-minute burst of radiation than from years of theoretical work. That is science at its best, reality surprising us, overwhelming our instruments, forcing us to revise our understanding of what is possible. The universe always has more to say than we expect, and the magnetars are saying it in the loudest possible voice, in frequencies we are only beginning to learn how to hear.